Hi everyone, in this video we're going to be proving some problems using the indirect proofs we learned in the last video. So let's get started. In these videos we're going to do something a little bit different. We're going to be proving the rules of natural deduction that we've been using all this time. So for our problem sets we're going to be proving rules like modus ponens, hypothetical syllogism, and so on. For this example in particular, we're going to be proving the rule of addition. So the rule of addition is if you have P, then you can get P or Q. And the reason that this is the case is because if one statement is true, then you can add on anything to it, and and it'll also be true because for the OR operator, only one of them needs to be true. And so if you already have a true statement, you're going to continue to have a true statement no matter whatever you add onto it. So that's the rule of addition. That's how it works. So we're going to try to prove the rule of addition. I'll just put it up here, addition. We're going to prove the rule of addition, or yes, we're going to prove it. So we're going to start using an indirect proof. So again, with our indirect proofs, we assume the negation of the conclusions. We get not P or Q, and this is our assumption for indirect proof. And from here, we can get not P and not Q, and we get this doing 2 De Morgans. From here, we can get not P. We get this using 3 simplification, and from here we can get P and not P, and we get this using 1 for conjunction. So as you can see here, proving this problem was pretty straightforward. Hold on. Well, before we talk about it, let's finish it. And so our conclusion 6 is P or Q. So we're just restating the conclusion. Our conclusion is P or Q, and we did this using 2 through 5 indirect proof. So as you can see, this was pretty straightforward. It wasn't too complicated. Most of the stuff was most of the steps were really easy to follow. So this problem wasn't too bad. Now I want to look at the comparable problem for doing this using a conditional proof. Slide down the camera. Okay. So we're just going to copy and paste this. Delete this. Okay. So let's see. All right. So let's get started using a conditional proof. Now, as I said in the videos with a conditional proof, you typically, if this was a conditional proof, we'd be assuming the antecedent of the conditional in our conclusion, but there's no conditional in our conclusion. So do we assume? Well, we already have P. We can try assuming Q and see where that takes us. But given that we have normally when we try to solve a problem like this, we, there's something pretty straightforward in the problem that we can assume, and we could try Q, but, for this video, I assumed P then Q is my assumption for indirect proof, and I did this essentially by guessing, because I saw P then Q, and I saw P, and then I see Q in our conclusion, so that's sort of where I figured it out. But again, it's not obvious at all in the problem that this is what you should assume, but it's what I assumed, and after struggling with it for about an hour, it got me to solve the problem. So I assume P then Q, and then from there you can get Q, and we do this using 2, 3 modus ponens. And from there, now that we have Q, we can get, if you assume P then Q, if you assume P then Q, then you get Q, and we do this using 2, 3 conditional proof. And from here, Yeah, normally when we'd be doing a conditional proof, we'd be done here. But as you can see, we didn't get our conclusion. Our conclusion is P or Q, and we don't have that yet. So we did a conditional proof, but we're going to continue this using natural deduction. So from here, we're going to get not P then Q or Q using for implication. From here, we're going to get not P or Q using 5 implication. And from here, we're going to get not oh, let me put this in parentheses. We're going to get not P and not Q or Q using 6 De Morgans. And from here we're going to get P and not Q, also in parentheses, P and not Q, or Q using 7 double negation. And from here we can do Q or P and not Q using 8 commutative. So I just want to take, I've gone through this really quickly, and I just kind of want to take a step to sort of slow down and make some observations. So as you can see, we're already in premise 9 so far, and we still haven't solved the problem. So that's one point I want to make. Using the conditional proof in this instance is a lot harder. 2, if you look at the actual sort of structure of how we've been proving it, there's a lot more going on in, premises 4, 5, 6, like 6 and 7. Like these are really complicated. Premises we have here, and there's a lot going on, and our ways of solving this are sort of advanced. So again, like this also contributes to it being harder. Point 3 is we're at premise 9, and we still haven't solved the problem yet. We haven't gotten to our conclusion yet, whereas we got to our conclusion 6 premises using the indirect proof. And so we've done some things. We did modus ponens using premises 2 and 3. And again, another point is our assumption for indirect proof wasn't straightforward, whereas our assumption for conditional proof wasn't straightforward, as it was we weren't sure what to assume when we were making a conditional proof, whereas the assumption for indirect proof in our indirect proof was really straightforward. It was just the negation of the conclusion. So again, just use your best judgment when you're trying to figure out these problems. As a typical rule, if a conclusion is stated not as a conditional, it's generally easier to use an indirect proof. And if it is stated as a conditional, it's generally easier to use a conditional proof. But again, if you're struggling with one, switching to the other might be easier, and they're both equally valid ways of proving it. So now that we've just stopped and we've made some observations, let's finish this problem. So in premise 10, we have we have Q or P and Q or not Q. And we did this using premise 9 distributive. And from here we can get Q or P using 10 simplification, and from here we can get P or Q. And this is our conclusion, and we're not stating a conditional proof because we did this using natural deduction. Yeah, so we did this using 11 commutative. And so again, this took us, so again, just, making some points, this was a lot harder to do than the indirect proof, and we had to use twice as many premises, and we had to use a combination of conditional proof and natural deduction to prove this rule of inference, which we use all the time. So it's really cool that we proved it, but again, it's a lot harder and less straightforward to prove it using a conditional proof than it is to prove it using an indirect proof. And so there's one, so generally, like I said, if there's a conditional in the conclusion, it's easier to use using a conditional proof, and if there isn't, it's probably easier to use using an indirect proof. So as you'll see, certain rules we're going to be using, like modus ponens, hypothetical syllogism. You can experiment around with them to see whether it's easier or harder to use a conditional proof, and whether using a conditional proof is shorter or longer. And then from there, when you're solving these problems, you'll have a sort of hunch as to which might be a better way to solve it. So this is our last video in our natural deduction section, and in the next videos we're going to be starting on predicate logic. So I look forward to seeing you then.